It is proposed to use the nuclear fusion reaction where two deuterium are combined together to give a helium nucleus. In a nuclear reactor of 200 megawatt rating, if the energy from the above reaction is used with a 25% efficiency in the reactor, how many grams of deuterium fuel will be needed per day? The masses of deuterium and helium are given to us. So if we begin with the energy requirement per day, so the value which we are given initially is 200 megawatt rating. So from here, if I begin my calculation, so I can begin by calculating energy requirement per day. So I am writing energy requirement per day, and this can be calculated as E, which is equal to P into T, and we can write it as 200 megawatt, that is 200 into 10 to the power 6 watt, and for time we are multiplying it by 86400 seconds, or you can say 24 into 60 into 60. So on solving we obtain the value in joule, and the value is obtained as 1.728 into 10 to the power 13 joule. So 1.728 into 10 to the power 13 joule is the value or the energy required per day. Now the next thing which we are calculating over here is energy released per fusion reaction. So energy released per fusion reaction. So if we calculate for the energy released per fusion reaction, so we are first of all we will calculate the value of delta m c square, or I can simply say that the energy can be calculated by calculating the mass defect, and then we can multiply it by 931.5, and then the value will be obtained in mega electron volt. So in order to do this, we are calculating the value of energy by calculating the value of mass defect. So to calculate mass defect, I write twice the mass of deuterium atom, that is 2 into 0.141, and then subtract it with the value of 4.0026. So this is the value of the delta M, and we multiply it by 931.5 to obtain the value in mega electron volt. In the next step, we can convert it into joule. So over here we obtain the value as 23.85 mega electron volt. So on conversion of this into electron volt and then into joule, so we can write it in 23.85 into 10 to the power 6 multiply by 1.6 into 10 to the power minus 19. So the value will be converted in joule. So on calculation, we obtain this as equal to 38.15 into 10 to the power minus 13 joule. So now using this result, that is energy requirement per day and the energy released per fusion reaction. So now we are calculating the number of fusion reactions required. So all we need to do is we need to divide these values. So now I am calculating the number of fusion reactions required. Number of fusion reactions required can be calculated by dividing the two values, that is 1.728 into 10 to the power 13 by 38.15 into 10 to the power minus 13, and we obtain a value equal to 0.045 into 10 to the power 26. So this is the number of fusion reactions required. The next thing, if we look over here, so the question is asking how many grams of deuterium fuel will be needed per day. So in order to calculate for the number of deuterium fuel that will be needed per day, so let us calculate the number of deuterium atoms required. So now we are coming for the number of deuterium atoms required. Deuterium atoms required. So I can say that the number of deuterium atoms involved can be calculated in this way. So we obtain the value of 0.09 into 10 to the power 26 atoms. So over here we have used the number of fusion reactions. So the number of fusion is 0.045. So 0.045 into 10 to the power 26, and in each fusion reaction we are using 2 deuterium atoms. So we multiply the two parameter to obtain 0.09 into 10 to the power 26 number of deuterium atoms that are required. So if we calculate the number of moles of deuterium atom, so the moles of deuterium atom can be calculated by dividing it by the Avogadro number. So we obtain 0.09 into 10 to the power 26 atoms divided by the Avogadro number, that is 6.023 into 10 to the power 23. So we obtain a value equivalent to 14.95 moles of deuterium atoms. So now we can calculate the mass in gram of deuterium atoms required. So mass of deuterium atoms required, and it can be calculated as 14.95 into 2, so that is equal to 29.9 gram. So if we come to this problem one more time, so the question is giving us one more data. The question is saying if the energy released is used with a 25% efficiency. Now since the efficiency is 25%, so we need to make sure that a larger mass is provided. So we need to do last calculation. So in order to make sure that the energy from the above reaction is used only with a 25% efficiency, so therefore I say that the actual number of deuterium required required will be equal to 119.6 gram. So we obtained this value 119.6 gram. So if you just divide 119.6 with 4, you will obtain 29.4. So what we have done is we have selected a particular number, say x, and then 25% of that weight is equal to 29.9. So we have obtained 119.6 gram. So this is the final answer for this particular problem, where it is asking us for the actual number of deuterium required.